All right, cool. So today we are going to be talking about, or more about describing our variables. But before we get into that, let's just look at the upcoming week's schedule. So today we're going to be talking about central tendency and variability and how to calculate these and what they are. Wednesday is going to be all about assignment number 8. Technically, after today, you'll have everything you need to do assignment number 8, so you can go ahead and get started on it after today if you really want to. So Wednesday is going to be an optional class. However, I highly recommend that you come because I will be showing SPSS. There is an SPSS component for assignment number 8. I will be walking through that, but just like on the graphs one, it tells you there are pictures that walks you through SPSS. So it's optional on Wednesday, but I would suggest that you come. And then on Friday, we're going to do a lecture on z-scores and probability. So you can see that we're starting to get more into um, statistics, this idea of statistics. We covered a lot of research methods prior. Now we're going to be jumping into statistics. However, don't become too worried. Pretty much everything that you've learned in middle school and high school is enough that you need to do these type of statistics. So don't freak out too much. Some important due dates. So quiz number 7 is going to be due Sunday at midnight, like typical. Um, it's not open yet. It'll be open at the end of on Friday's class, but just putting it out there. Assignment number 8 is going to be due Wednesday at midnight. And then assignment number 7, which is that intro assignment, is going to be due July 4th at noon, so Sunday at noon. All right, so this is just a quick and dirty schedule. All right, so let's jump into it. So this should be review from either last class or the class before that, but this idea of descriptive statistics. So what are they? What's the point? Well, we want to summarize, organize, and simplify our data in a meaningful way. So we're interested as researchers in what our data looks like for multiple reasons, but it also allows us to summarize data for others in ways that they can read it. And let me show you an example of this, why we want descriptive statistics. So can you see this SPSS output? Or yeah, the data set. All right. So this is a real data set from a grant that I'm on. And I'm just going to scroll through really slowly and just to show you all the raw data that's on this. So it turns out that we actually have 374 teens, and we have parent data for each of those teens. And in total, we have like over 5,000 variables. Yeah, so there's over 5,000 variables in this data set with over 374 participants. So you can see there is a lot of data. And if I were to give you this data, right, I'm a researcher and I give you this data, you're a reader of research or whatever. This isn't all that useful, right? This is raw data. And so let me go to a specific variable, CDI underscore T. Okay, so this is a depression variable, this one that I have highlighted. And just on a scale, like we just asked participants a bunch of depressive symptoms questions, like have you experienced this symptom? And it gives us a total, and we add it all up, and it gives us a total score, I think ranging from like 0 to 45, where 45 or whatever the high number is just lots of depressive symptoms, right? So you can imagine the higher the number, the more depressive symptoms someone has. So let's say, like in your homework assignments or in the examples I show in class, I give you all of these data points, right? Just this variable, depressive variable. Once again, it's really not that useful for you. It's like, sure, okay, I can see all of these. I could see what this participant said, but it's really not that useful for you. Well, if I run some descriptive stats, and I've already done it, but it's like literally 2 clicks of a button on SPSS, and we'll get into how to do this on Wednesday or on assignment number 8. But we can see with these descriptive statistics, it actually is a lot more useful, both as me as a researcher and for you. So we can see that, the average was 14.4 depressive symptoms out of like 45. So relatively low. So right off the bat, just by looking at this mean number, I know that, okay, on a scale of 0 to 45, I think it's 0 to 50, let's just say 0 to 50, 14 is relatively low, giving me an idea about the distribution of my data. All right, Mode I don't really care about, and we'll explain why we don't really care about mode for this type of data in a little bit. But I see that, and we'll get into what standard deviation is, but there's this measure of skew. And don't write this down, you don't need to know this yet. But I know that since this number is above 0.5 and it's positive, it means that my data is actually really skewed. And so I haven't looked at the graph yet, but I can imagine that, and it means that it's majority of the data is on the left end, so the lower end. So I know that a majority of my participants scored on the lower end of my depressive symptoms, just by these descriptive stats, right? Just by a couple numbers here. And now I can see the range. So I could see the minimum value was a 2. So at the least amount of depressive symptoms on my participants was a 2, and the highest was a 41. And remember, the scale is on a scale of like 0 to 45, 0 to 50, I believe. So I can see the range and the minimum and maximum. And then the percentiles. Remember that box and whisker plot? I could see the 25th percentile and the 50th and the 75th percentile. So just by looking at some of these numbers, as a researcher, I can get a really good idea about my data. And I actually plotted it out just by doing a histogram, and I put a normal curve. And what you can see is, and we'll show it again in a couple of slides, but this data is skewed. It looks like a lot of participants are on this left-hand side on the lower end of amount of depressive symptoms. So it gives us, and not many participants are up here, right? If you look at this curve, it's not symmetrical. More participants are over on the left-hand side, meaning it's skewed. So this gives me, as a researcher, this gives me a lot of good ideas about what this particular variable looks like. And now mathematically, there's a lot of things I can do as a researcher. Like if it's too skewed, I can like transform it. Not going to get into that. Just know that these descriptive statistics allow researchers to get a good idea of what's happening with that variable. And it also allows us, the second point, to summarize it in a useful way for others. Remember that those raw data points that don't mean anything to someone who doesn't have a computer program to run the stats. But a mean does, right? The average does tell you something about your data. If it's skewed, it also tells us something about our data. So this is why we do these descriptive statistics. It tells you a lot about your variables. The appropriate technique, whether we use mean, median, mode, or some of these other ones, depends on the measurement scale, but we'll get into that. Okay, so this should just be a review. Not going to get into how to find the individual answers, but this is a frequency distribution table. Make sure, go back to the previous lecture, rewatch if you have to, but make sure you're able to know what each column represents. So X is just your raw data points. F is frequency, just how often they occur. Cumulative frequency, it adds it up as we go up. So we know, and if 15, that we know that 15 participants had a 3 or less. And there's multiple ways to figure that out. You can add up just the frequency, very simple, or the cumulative percentage. So it's just a frequency in percentage form. So make sure you know each column and be able to answer questions like, oh, what does a 15 represent? Or what does this column represent? So something that we talked about in detail last class. So just make sure you know this. And this should also be review. But today we're going to be going over central tendency, which is just the typical representative score that represents the middle or the average of the distribution. Once again, we talked about this in this exact slide in a previous class. Variability, so we're also going to look at variability in the second part of today's lecture. And variability is just a number that indicates how much scores differ from one another. So, if there's low variability, well, I'm not going to explain too much. We'll get into that later. But we could have things like low variability where our data is all scrunched up around one mean. Or we could have high variability where we have, we have a lot of people scoring around the average because that's what an average is. But we also have a lot of scores that on the higher end and the lower end. So we can have high variability and low variability, but we'll get into that in a little bit. Then we can also have skewness. We talked about skew before very briefly. We can have, if it's not skewed, we have a symmetrical distribution. So if I put a line right down the middle where the mean, median, and mode would be, we can see that it's equal on each side. But we could also have positively skewed and negatively skewed. Like in this example with the depressive symptoms, it was more positively skewed in that most of the data points fell on the low end And we had a couple not outliers, but there was less people on the extremes. Negatively skewed is the exact opposite. More people scored on the higher end and less people scored on the lower end. So this is an idea of skewness. You just have to know the general idea that, what positively skewed and negatively skewed are. You don't have to know how to calculate that stuff. All right, and this is just, why do we describe this data? Why are we doing these descriptive stats? Like I said, skewness, variability, and central tendency, all of these descriptive statistics all communicate what the data is like. You can't get a sense of what the data is like just by looking at the raw data points. You need to use these descriptive statistics. All right, any questions so far of this overview before we get into specifics? All right, not seeing any questions. So let's jump into central tendency. So the central tendency is just the typical score in a distribution, and we can figure this out in a couple different ways. So we could do the mean, which is just the mathematical average of all the scores. We could use the median, which is the middle score in a ranked order distribution, or we could use the mode, which is just the most frequently occurring score/category in a distribution. So I'm not going to go into how to calculate each of these because I'm going to assume that all of you know how to calculate the mean, median, and mode. But there are some things I would like to point out that are really important to know in terms of psychological research. So once again, mathematical average is the mean. You all know how to calculate the mean. You take the sum of the scores and you divide by how many scores there are, right? But in psychology, we can have two different types of mean, and they're both calculated the same way. The only difference is the symbols that we use to denote what we're talking about. So it's important that you know what these symbols are and what differentiates sample mean versus population mean. So in a sample mean, we use this capital letter M to represent sample mean. So whenever you see an M, a capital M, know that we're talking about the sample mean. And how do you calculate the sample mean? Well, you just take the sum of the scores. So if you remember X, going back to a graph like this, X is just the raw scores. So you take the sum of those scores and divide it by the number of scores, right? How you do average. This is what this symbol means, is this Greek symbol, sigma, I believe. It just means sum. So you just sum up the scores divided by the total number of scores. And in the sample mean, it's just a lowercase n. Don't ask me why, it just is. So population mean is the exact same formula, except this time we use this weird Greek like U symbol to represent the population mean. And instead of a lowercase n, it's an uppercase n. Once again, really all that you need to know is how to find the average. It's the same between the sample mean and the population mean. The only difference is sample mean is a capital M, population mean is this weird U symbol. All right, so if I were to ask you in an exam or a quiz, is this, and I showed you this formula, and I said, is this a sample mean or is this the population mean formula? That's what you would have to be able to tell me. All right. And typically, I'll give you an example of both, but typically we always use the sample mean because we, as psychological researchers, typically don't have access to the entire population, but in some cases we do, and I'll show you what I mean. So not going to walk through this. This is just calculating the sample mean. You can see that this is just a sample of psychology faculty salaries, and what we have 9. So you add up all 9 salaries, divide it by 9, and we find out that the average salary was $66,000 per year. Come back to this slide if you need a refresher on how to do mean. So this is an idea of sample mean. Well, we could also look at the population mean, which is the exact same formula, right? Same process. But in this time, instead of just looking at a sample of psychology professors, we look at all, 7 journalism faculty members of faculty. So, we could look at all WVU journalism faculty members and find the population mean. It wouldn't be a sample because we have all of the population. So we don't, the sample is the entire population. So this is an example of sample versus population, right? Typically doesn't happen a lot in psychological research because we're always using samples and not the full population, but it could occur, and here's an occasion where it could occur. Interpretation and formula is the exact same, except for these two symbols, the capital M and this weird U shape. All right, median. Just the middle score in a ranked order distribution. We're able to say, hey, exactly 50% of the scores fall at or above the median. Conversely, you could also say 50% of scores fall at or below the median. It just splits your data in half. To find the median, just put it in order, whether it's from low to high or from high to low, doesn't matter, and find the middle score of that distribution. So once again, not going to walk through it, but we put all of these ages in order from least to greatest, and we just found the middle. Right. Now, what if there's 2 in the middle after you've, I don't know how people do it, but I always just say, okay, I cut off 7 and 0, I cut off 3 and 1. Oh, here's our middle, 2 and 1. Just find the average or the middle of these two numbers. So we know that the median is 1.5. Okay. Any questions about mean and median so far? Pretty straightforward stuff. If you need a refresher on how to calculate it, come back to these PowerPoint slides or look it up on Google. All right, mode, also fairly simple. It's just the most frequently occurring score category in a distribution. We can see, you just count up the frequency of each one, and the mode is which one happens the most. So we can see the mode is 6. And then whatever, our interpretation is, it looks like more people ate 6 restaurant meals during the last week than any other amount of meals. So this is a number form, but it could also be in category form with just words. So we can see that people's most favorite restaurant is Black Bear Burritos. So more people chose Black Bear Burritos than any other. You can also have more than one mode. So you can have 2, 3, 4, 5, 6 modes. You can have as many modes as possible. And the interpretation is still the same, right? More households have 0 or 1 child than any other number. So you can have more than one mode. You can also have no modes. So maybe none of the categories are the most. Perfectly fine. You would just say no breed of dog or whatever you're studying was more preferred than any other. So you can have no mode, you can have more than one mode, or you can have one mode. Pretty self-explanatory. So briefly, I just want to talk about relationships between mean, median, and mode, and this idea of distribution. So here's an example of a symmetrical unimodal distribution. So what does this word unimodal mean? Well, it just means one mode, unimodal. So we can see if our data is symmetrical and we only have one mode, the mean, median, and mode are going to be the same number, right? The average is right here. The mode is also the top of this line, and the median is right in the middle because it's symmetrical. So if we can imagine 50% of the data falls over here, 50% of the data falls over here, mean, median, and mode are the same in a symmetrical unimodal distribution. But we don't always get these types of distribution. You could have 2 modes. So what happens if you have 2 modes? So you can see the graph, this histogram of our data, this plot of our data. And we can see we have 2 humps. And so we have 2 modes. Now, because it's still symmetrical, our mean and median are still directly in the middle and the same numbers, right? 50% of our data falls over here, 50% falls over here, and it's symmetrical. So our mean and median are the same. This doesn't really happen, in real world, this doesn't happen all that often, right? No data in real life is ever truly symmetrical, but it can get really close. And what this actually might represent is, so if you have 2 modes, it might tell you, oh, hey, there's 2 distinct groups in our sample. Just imagine if this was if I calculated, if I asked how long do you spend on social media, and I plotted it out, and we find out that there's 2 modes. One mode is like 30 minutes. So not how long do you spend on social media throughout the day? 30 minutes, not that much, but there's another mode of 2 hours. And so we can see, hey, we have 2 distinct groups of people in our data set. We have those who don't really use a lot of social media and those who do use a lot of social media, and they're actually evenly distributed, right? So that gives you a sense of what our data looks like. Once again, it doesn't happen all that often where it's symmetrical. Now, here's this idea of a skewed distribution. And it messes with our median and our mean. And I'm not going to go too much into why, like the mathematical reasons why, but I think these graphs make it a little bit more evident. So we still have our mode, which is the peak, right? That should be fairly simple. Whatever the peak is in your graph, that's going to be the mode because the most amount of people said whatever this value is. But because this is skewed, and it's skewed, it's a positive skew, so most of our scores are on the low end. But we do have this, like, I'm not going to call them outliers, but I'm going to call them these extreme scores. So these extreme scores on the high end are going to drag our median and mean closer to the high end. Now, if you could imagine, if the skewness was reversed and most of our scores were on the high end, but we had some extreme low end scores, it would drag the mean and median closer to the low end. So what you really need to get out of this graph is a skewed distribution messes with our mean and our median. When it's symmetrical and it's not skewed, our mean and median are going to be the same. Because there's two modes, our mode is also not going to be the mean and median. But if it's symmetrical and there's only one mode, all of our values are going to be the same. So what you really need to get out of that is a skewed distribution messes with our median and our mean. Don't need to know the mathematics behind why, just know that it does. Okay, so here's some things to think about when deciding on which ones you're going to report. So you need to think about your scale of measurement. So for a nominal scale, things like gender, right, or these plain categories where order doesn't matter, you would want to use the mode. And I want to show you an example of why. So this is actually something that's going to come up later as well. But SPSS, it's really smart, but it's also really dumb. And it will do whatever you want it to do, whether it should do it or not. So here's an example of, let's see, do I have it? Yeah, right here, I have average. Okay, so remember in SPSS, I was talking about you have to put numbers to categories. And in some situations like nominal variables, it doesn't matter what the numbers are. So for gender, we had to code males as 1 and females as 2 in this data set. Well, if we're looking at measures of central tendency, I could find the average, right? It's all just numbers, it's all just math. And I find that the average is 1.51. Can someone interpret what an average of 1.51 means when it comes to gender? The answer is no. Don't even attempt to. You can't. I mean, you technically can mathematically, but like the average doesn't mean anything in this nominal variable. Our numbers could mean anything. I could put males as 573 and females as 2, right? And that's how we coded them in our data set. It doesn't matter how we code them. So therefore the range doesn't matter. I mean, excuse me, the average doesn't matter. What does matter is the mode. So we find out that the mode is 2, which means female, because that's how we coded things. So we know that there are more females than there are males. And if we come down here to this graph, we can see, don't worry about the normal distribution, but we can see that, oh, okay, there are more females, which is a 2, than there are males, which is a 1, ever so slightly. So hopefully this shows that, like, with a nominal scale, the median or the mean doesn't mean anything, but we care about the mode. In an ordinal scale, we typically use the median, but we could also use the mode in some situations. So if you think about an ordinal scale could be, oh, are you a freshman, sophomore, junior, or senior? Well, we could find the median, and it would tell us like what the middle is, but what we probably care about is the mode, right? What is more in our sample? Is it more freshmen, more sophomores, more juniors, more seniors? So it really matters what variable you're actually what you're measuring and what you care to figure out from that. Interval or ratio scale, you're typically going to use the mean. You could use the median or mode. in some situations you could use the mode, but here's an example of why you wouldn't want to use the mode. So here is a distribution of all the depression scores in our sample. We can see that 7 people said two depressive symptoms. 14 people said 12. It turns out that the mode is actually 5 depressive symptoms with 17 people. Conceptually, do you care that 17 people said 5 depressive symptoms, but only 16 people said 7? Like conceptually, you don't care about that. Like, why would I care that on a scale of 0 to 43, right, or 0 to 45, why do I care that 17 people said 4, or 17 people said 5, and 15 people said 6? Like, it's not useful information. The average is useful, right? What is the average amount of depressive symptoms? That's useful, but mode really isn't. So you really got to think about your variables. And this actually might have been a problem in some of your homework assignments where you came up with graphs. Some of your graphs just don't make sense. Like if you were to do a pie chart of all of this, you would have 43 different like slices, and like it just doesn't make sense. Like, why do I care about that information? Now, a pie chart of gender makes sense, so you can see the breakdowns of gender, but a breakdown of every single amount of depressive symptoms just doesn't mean anything. So you really got to think about your own variable. All right. And that gets at this point number 2. Think about what you most want to know. If you want to know the most frequent score, the mode, obviously. If you want to know the most typical score, median or mean. All right. Any questions about central tendency? I know we went over a lot, but I think it's fairly simple, like especially how to calculate things. Really, the big things that you need to know are how to do mean, median, and mode, which hopefully you all know, and what some of these symbols mean when in terms of population mean and sample mean. All right, so let's go to the next PowerPoint, and this is going to become a little bit more complicated, but hopefully not. All right, let's from the current slide. All right, so we talked about central tendency, which is this idea of mean, median, mode. Now we're going to talk about variability. So this is taking it one step further. Once again, we want to summarize, organize, and simplify our measurements. Descriptive stats, it still falls under descriptive statistics. But now we're going to be focused on variability. So variability, essentially, these measures of variability, and we're going to cover a few, summarize the spread of scores in our distribution. So we're seeing how far our scores are spread out. So they can measure how much the scores differ from one another, especially in regards to range. But they also measure how much scores differ from the center of the distribution. But we're going to get into that in a little bit. So some of the things that we're going to be talking about today are range, semi-interquartile and interquartile range, and variance and standard deviation. So let's jump into it. Actually, let's jump into why is this important. So we know that behaviors, thoughts, and emotions, so things that we care about in psychology, vary, right? They're never they can vary. So they vary among individuals. So my amount of depressive symptoms are going to differ from your amount of depressive symptoms. My personality is going to differ than your personality. Energy levels, emotions, whatever. People are different from one another. People are also different in certain situations. So your energy level sitting here at 2:00 p.m. in a Psych 203 class is probably a lot different than your energy levels on a Friday afternoon. So it differs across context. It can differ across time. If I were to measure you at 5 years old and 25 on memory recall, you're going to vary, you're going to differ. So variability measures capture these differences, and these differences are central to understanding psychology. And this gets at this point number 2. Variability measures form a crucial part of inferential statistics. So inferential statistics, what we're going to cover later in the semester, allows us to say, hey, here is the relationship between 2 variables in our sample, and we think this is what it looks like in the population. So let me show you an example of why variability is really important. So let's take this idea of depression and these depressive symptoms. A lot of times in psychological research, one of the things that you try to do is you try to predict a variable. So let's say we're going to predict depression. I want to know what causes depression. And ignoring research methodology, right? You can do a bunch of different designs. Let's say I identify 3 variables that I think predict depression later. I'm going to say social media addiction and 2 other variables. It doesn't matter, right? I think these variables predict depression. Well, what happens if I take a sample, right? I collect data, and it turns out that everyone in my sample scored around a 14 or a 15 number of depressive symptoms, right? Let's say like 90%, 95% of my sample scored a 14 or 15 out of a scale of 0 to 40 on my depressive symptoms. So there's really no variability. Everyone is in this range of 14 to 15. Well, the whole point of trying to predict something is I want to predict what causes people to have high depressive symptoms, what causes people to have low depressive symptoms. Well, I can't predict that if I don't have any people who have high or low depressive symptoms in my sample, right? If everyone is about the same, I can't predict what causes people to be different if everyone is the same. So this is why understanding variability or looking at variability of your measures and reporting on it is very important. Because there's things that we can do behind the scenes that I'm not going to cover. Let's say if it's too skewed, I could do a log transformation. You don't have to know that, but there are things I can do with my data if it is skewed or if there is low variability to fix them so that we can run some analyses on it. But that is the big importance of understanding variability. If we don't have variability in our sample, we can't use that to predict things, or we can't predict that low variable. All right. Any questions on why understanding variability is important? Hopefully my depression example made sense. You can't predict something if it's not in your sample. You can't predict high depression if you don't have people who are highly depressed. So we want a good range of participants who are low depressed, average, median depressed, and high depressed. We would like a good range. All right, so let's jump into range. Well, let me back up. I didn't mean to say range. I meant we have a good distribution of high, medium, and low depressive symptoms. Range and that distribution is a little bit different. So let's jump into range. Range is exactly what you think it is. It's just the highest score minus the lowest score. The characteristics of the range, it only depends on 2 observations, the lowest and the highest. So it's really distorted by outliers, right? It would say using a depressive sample, if a majority of my participants fell between 14 and 16 depressive symptoms, but I had one participant say 50 and one participant say 0, I would say, oh, my range is 50. But in reality, only one person scored up that high and everyone else is really, really low. So it can be really distorted by outliers. So when do you use range? When you need a quick and dirty measure of variability. In the real world, while you report range, maybe in your methods section, you say, oh, scores ranged this and this. No one really looks at your range and says, oh, I can really understand your data. But it is a quick and dirty way as a measure of variability to see how far apart your high scores and your low scores are. Gives you an idea of the distribution. All right, so I should say I'm going to go through range and interquartile range, and then we're going to show an example of it. So the interquartile range, and this is going to, I think, make a lot more sense when I plot it on a box and whisker plot, or I guess I show it on a box and whisker plot. But an interquartile range is the distance between the first quartile, so that 25% point, and the third quartile, so that 75th percentile point in your data. So it's the range covered by that middle 50% of your sample. And so you just take Q3 minus Q1, and we'll get into where you find those numbers in a little bit. But the semi-interquartile range is just the IQR divided by 2. And it tells you the typical distance from the median. So you just take Q3 minus Q1 divided by 2. All right, so let's just get some characteristics, and then we're going to show an example of this. So characteristics of the IQR and the semi-interquartile range. So it's based on that inner 50% of the distribution. And this will make, I think, a little bit more sense when we look at that box and whisker plot. It's less influenced by extreme scores than standard deviation and variance, which we'll get into. And it's a useful measure of variability for skewed distributions. Not going to go into the mathematics of why, but just so you know, if you're doing a skewed distribution, it may be more relevant to report the interquartile range than, let's say, standard deviation. But let me throw it on this box and whisker plot. So hopefully this box and whisker plot is familiar. We have our minimum, we have our maximum at the very top. We have Q1, which is that 25th percentile. So 25% of scores fall at or below this value. The median is at 50%, so 50% score below. 75%, 75% of the values score at or below Q3. Or conversely, you could say 25% score above Q3, but I think it's easier to conceptualize doing that at or below. So the range is just that max value minus the min value, so that range over here, and encompasses all of the data. The interquartile range is just Q3, so that 75th percentile, minus Q1, that 25th percentile. And that SIQR is just the IQR divided by 2, and it tells you how far away people stray from the median. So here are these basic calculations just on this slide, so that way you can come back and you can go to one slide to figure this out. Not going to go through it because I've already talked through it, but let's show an example of this using data. So on the left-hand side is just the raw values, and on the right-hand side, I just ordered them. I put them from least to greatest. So we can find the median. And we've already talked about how to find the median. So it turns out that the median is 2.5 in this one. Again, if you don't know how to find the median, go back to a previous, look it up on Google, or go back to a previous PowerPoint. But that is the median, 2.5. So we have this dash representing the median point. Well, now we just got to take the median of the lower half, and that gives us Q1. So we do the median again, and we find out that the median is a 1. Number, it looks like we're studying number of friends. So we know that 25% of participants had 1 friend or fewer, but we could also say Q1 equals 1. Let's do it for the top half now. So we know that the middle of the top half is a 7. And so that's Q3, or our 75th percentile. So we know that 75% of participants had 7 friends or fewer. So we've identified the median, we identified the Q1, we identified Q3. Now let's get into some of our stats. We can find the range. We just take the max minus the min, right? Max minus min. So we have a range of 10. And we can read down here, the interpretation is the difference between the least and the most number of friends was 10, right? Range, relatively simple. Now let's find the interquartile range. So if you remember, we take Q3, or that 75th percentile, minus Q1, that 25th percentile. 7 minus 1 is 6. So the most typical 50% of our participants, right, that middle 50%, differed in their number of friends by 6. So that highest 50% and that lowest 50%, if that makes sense, differs by 6. So if we go back up to this box, the difference between this top Q3 and this Q1 is 6 friends. That's what that's showing. Okay, so that's interquartile range. And then the semi-interquartile range is just 6 divided by 2. So that interquartile range divided by 2, and it's 3. So a person's number of friends most typically differed from the median by 3. So we know in that distribution, in that 50% distribution right here, right, that orange, people differed from the median on average by 3. So they strayed from that median by 3 number of friends. All right. Any questions about calculating interquartile range, semi-interquartile range? Right? If I give you this raw data, you should be able to put it in order, find the median of the lower half, find the median of the top half, do some really basic subtraction, and tell me interquartile range, semi-interquartile range, mean, median, and mode. And that's something you have to do for your homework assignment. All right. Let's move on to something that's a little bit more complicated, and that's the idea of variance and standard deviation. Okay. So you're going to see here some really, in my opinion, scary looking formulas. I hate formulas, and I don't resume recording. So what I really want you to get out of this is, I'll get to what I really want you to get out of it afterwards. All right, so let's go into variance and standard deviation. So variance is this idea that scores differ from each other, right? We've already established that fact that no one's the same. So scores differ from each other and they differ from the mean. We're interested in how far away am I from the mean? So think about an exam, right? I give a test to you guys and you might be curious for yourself, well, how far away am I from the average student, right? What is the average grade? How far away is my grade from that average? So this is an idea of variability. So the variance mathematically is the average squared amount that scores differ from the mean. And this will make a lot more sense with an example. But what you need to know is a bigger number means that data is more spread out, and a smaller number means that data is more concentrated. At the very bottom, you can see here are two formulas, one for the sample variance and one for a population variance. Remember, there's a difference between sample and population. There's some really minor differences in the formulas. Once again, you just got to know the differences. So sample variance is denoted by S squared. Population variance is this weird, I think it's like omega, I forget what it actually is, this symbol squared. And for the most part, the formulas are the exact same, right? You have the sum of squares, or the sum of all the raw scores minus the average, and we'll get into this. But the sample mean and the population mean, right? That capital M, that lowercase weird looking u, sample mean, population mean. And then we will eventually, whenever we divide it, have to divide it by the number of scores minus 1 for the sample variance, and for the population variance, it's just n. You don't need to know this. I just want to show that there is a slight difference between the two. You don't need to know it. So I'm just going to move on from it because it's too much to really get into it. All right, so that's variance. And standard deviation is very similar to variance. It's actually almost the exact same, but this really important part right here, the output for standard deviation is in the units of the variable. And that doesn't make sense right now, but it's really going to make sense with an example later on. Just know standard deviation and variance, relatively the same thing, but standard deviation is more important for us. So once again, it's the average amount that scores differ from the mean. Bigger number, more spread out, smaller number, not as spread out. And to find this out, you just take the variance and you take the square root of it, and that gives you the standard deviation. All right, enough of the formulas, enough of this. Let's actually show an example. Oh, actually, this is just the idea of low variability and high variability. So let's look at this, and I've talked about this, but let's look at this the red graph. So this red graph is plotting data points that have really low variability. So like I said, the mean is directly in the middle, and most of the scores revolve around that mean. There's not a lot of variability. Let's look at this high variability, this green line. You can see that sure, that majority of people do fall under or close to that mean, but we have a lot more high values and a lot more low values. Things are more spread out. All right. Okay, so this is just some characteristics of variance and standard deviation, and hopefully this is starting to make more sense as we go along. But if all the scores in a sample are the same, right? If all of our depression scores are 14, or all of an exam scores are an 80%, the variance and standard deviation are 0. Now, you'll typically never see this in the real world, right? Not if you measure something, odds are that your participants vary somewhat, whether it's a lot of variation or minimum variation. No one ever scores the exact same. But if they did, and they didn't vary, variance and standard deviation would be 0. The more they vary, the bigger the numbers. But it's not influenced by the mean. Variance and standard deviation are not influenced by the mean. And I'll give you an example of that later. So here, I'm going to walk through how to calculate variance and standard deviation. So this is very important. Not that you memorize the formulas, but you can do it if I were to give you this table, because that's what's going to end up happening. You're going to be given this table, like in the frequency distribution, and you're going to have to calculate things. So let's walk through it. So first off, we have to find the sample mean. We've already done this many times. You can find the mean. So what do? You add up all of these scores, which I've already done, 483, and you divide it by how many total scores that we have. So we find that and we're looking at the height of basketball players. So we find that the average height is 69 inches. Hopefully all of you at this point can calculate the mean of a sample, of a set of data points. So we calculated the mean. Okay. So now we have to do the meat and bones of variance. So we calculate the mean is 69. In this second column, all we're doing is taking the individual data point minus the mean for each of these variables. So in this first one, we would do 62 minus 69, and that gets us -7, right? All I'm doing is taking x minus m. I even give it to you, and I believe, let me look at the homework assignment. Yeah, even in the homework assignment, we give you this x minus m. So we know that x is these raw values. M is, are you going to be allowed to use a calculator? Yes, you will. You will have a calculator. But yeah, you will have a calculator. But like I said, these aren't really that complicated. So it's not like you're going to have to be doing a lot. But yeah, so basic addition, math, squaring, yeah, you have a calculator. Okay, so I'm taking x minus m, 62 minus 69, our mean, which we already calculated in the prior step, -7. And now I'm going to do that for every single one of our data points. 70 minus 69 is 1. 69 minus 69 is 0. 66 minus 69, -3. And keep the negatives. So the negatives are fine. And what you're going to notice, actually, and this is a way to double check yourself, to make sure you did the calculations correct. If you add up this column, it should equal 0. And I'm not going to get into mathematically why it should equal 0, but these are all just how much they vary from the average. So if you average them all together, it should be 0, because that's what an average is. You don't need to know that. Just know that if you add up this column, it should be 0 every single time. The second column should be 0 every single time when you add it up. A good way to double check your work. Okay, so now we move to the next column. What do we have to do? Well, always within rounding, it will be 0. So like, if you make some weird rounding choices, it might be like 0.2, but rounding aside, it will always be 0. So now what we have to do is just square this number, right? The next step is just x minus m, which you've already done, squared. So it's just a squared difference. So -7 squared is 49. Because we're squaring, it'll always be positive, right? 1 squared is 1, 0 squared is 0, -3 squared is 9. All right. So we squared every single one. Now we just add them up again. And now we get a total of 160, right? So I squared all these differences, and our total is 160. So I throw it into our formula. So actually going back, what I just did is this numerator. I just did the top portion, right? I found x, we have all the x's. I found the difference, x minus m. I square them, x minus m squared, so that is that. Now I just got to add them all up. We got 160 divided by our number of scores minus 1. So we have 7 scores, 1, 2, 3, 4, 5, 6, 7, minus 1. So it would be 160 divided by 6 equals 26.67. So that is our sample variance, 26.67. Now, I could ask you, but it's going to show you, how do we find standard deviation? We just take the square root of that. So the square root of 26.67 is 5.16. Now so hopefully you've seen how to calculate it. We got the standard deviation. What does a 5.16 mean? Okay, so our interpretation is, on average, the basketball players differed from the mean height by 5.16 inches. So on average, all of our basketball players differed from the average, which was 69, by 5.16 inches. I want to show this on a graph because I think it makes a lot more sense. And this is something I added in. I'm not sure why they don't typically do this during normal semesters, but ignore the red text for right now. And has anyone ever seen a normal distribution plot like this with these standard deviations at the bottom? Give me a thumbs up or a thumbs down in chat and whatever you want. Have you ever seen this before? Oh, cool. Okay, cool. Okay, so it seems like at least the people that participated or at least said so, majority of people have seen this before. All right, that's good. Okay, this has actually become this idea of standard deviations, and this is going to become a lot more important on Friday when we talk about z-scores. But standard deviation is useful in this on this graphic. All right, so I don't know how much like in previous classes you've gotten into this, so I'm just going to give a really brief rundown. But we have our mean directly in the middle, right? We have this symmetrical unimodal distribution. Our mean is directly in the middle. And actually, it doesn't matter if it was symmetrical or not. You could still plot it like this. But anyways, it means in the middle. And we know that plus and minus 1 standard deviation, we know that 68.3% of our participants falls between plus or minus 1 standard deviation. This is in any data set. This is a universal rule. Plus or minus 1 standard deviation, 68.3% of participants fall within that. Now, if we go to 2 standard deviations, so plus or minus 2 standard deviations, 95.5% of our data falls in between those two numbers, whatever those numbers are. And then 3 standard deviations, 99.7% of our data falls in between these two values. Okay, so, and this is actually going to be, this is going to put you a step ahead for the z-score stuff that we talk about. But let me plot in this information that from the example that we just did. So we know that the mean is 69 inches tall. And we figured out, right, in this formula, that the standard deviation is 5.16. And I could give an interpretation of what that 5.16 is, but in reality, we know that 1 standard deviation unit equals 5.16. Okay, so I know that my mean is 69 inches, and I know that plus 1 standard deviation unit is 5.16. So I know that plus 1 standard deviation in our data is 74.16 inches. All I did was add 5.16 to the mean. Now, if I wanted to do plus 2 standard deviations, all I have to do is add 5.16 to this, to the plus 1. I could do the same thing for the plus 3 standard deviation. All I did is add 5.16 inches to this. And now I did the exact same on the other side, but just subtraction. So if you imagine, now I just plotted out all these inches that people reported and where they fall out in the data. So I know, and this is why standard deviation is really useful. Like this interpretation right here, on average, basketball players differed from the mean height by 5.16 inches. That's somewhat useful information. It's like, okay, what is really useful is plotting it on this chart. So we know that within 1 standard deviation, so 68% of our participants in our sample falls between 63.8 inches and 74.16%, 74.16 inches in height. We know that 95.5% of our participants falls between 58.6 inches and 79 inches. So we can start to figure out, okay, well, if we care about 1 standard deviation, 68, a good chunk, right? That middle group of our participants falls between these two values. All right, so that is why standard deviation is important. I believe that's it. Yeah, that's it for the lecture. But hopefully you understand this interpretation of standard deviation, right? It's just, on average, people vary by that amount from the mean. Whatever this value is, right? Calculating it using our formula, people value on average, people differ on average this amount from the mean. However, it's much more useful, and you won't have to do it for your homework assignment. This is for later in the semester. Actually, I think later in the week or next week, but you could plot these on a graph, and it tells you a lot more information. And that is the main use of a standard deviation. Are people confident that if I were to give you this, just these raw values, can you calculate sample variance and sample standard deviation. All right, for those, so that's the end of lecture today. Don't go just yet. Everything that I talked about is on a homework number 8. I haven't put it up yet. I'm going to put it up after class. Let me just show you what it is actually. So this is assignment number 8. You have a data set right here. What you need to do is just calculate central tendencies by hand. So everything highlighted yellow is where you need to put an answer in. I did that throughout the entire assignment, just so that way you know where to put answers in. If I don't see an answer there, I'm just going to mark it wrong. It's the only way I can do this by grading so many of them. Just make sure they're in this yellow spot. Anyways, what you need to do is calculate some modes based off of this data. It should be fairly simple. Calculate the medians of this data, calculate the averages from this data. Then you should be able to calculate the range IQR and SIQR for these. Should be able to calculate the range IQR and SIQR for this data as well, right? You have to order them all. Then you find that median, find the median of the top half, find the median of the bottom half, and do the subtractions. So that should be, all this should be relatively straightforward and simple. Then you're going to have to calculate the variance and standard deviation for this. This is just like in the example that I just did in this lecture. We give you the raw data over here. All you need to do is find the mean, right? Sum them up, find the mean. Subtract this number from the mean, square it, add up all of these squares, and then just plug them in, right? You would do all of these divided by n minus 1, and then you can also find the standard deviation by just taking the square root of that. So you put the two answers here for the sample variance and the standard deviation. Then that's it. You don't have to interpret anything. You don't have to put them on a graph. It's all you have to do. So if you don't feel comfortable with that, go back to this recorded lecture and walk through it again with this example. All right, so that's the first half of the homework assignment. The second half is doing this on SPSS. So there's a data set, just like with the graphing, a sample data set that you have to do, or you have to download, and it walks it through how to find everything, like how to find the mean, median, mode, all that information, all the descriptive stats. It walks through it. What you have to do is answer the questions with this. And there's just a bunch of questions that go along with it, like mean, median, and mode, blah, blah, blah. And now you don't have to calculate these things, right? You can just look off of the SPSS output. So you can do this all tonight if you wanted to. However, I will be on Wednesday at the beginning of class going through the SPSS output and explaining where to find this information. It is relatively simple. It does tell you in SPSS. Actually, let me just show you an example of the output. Like we said, it tells you the mean of the variable. It tells you the median and mode. It tells you all the information. So for the most part, you should be able to figure it out on your own. However, early Wednesday in the lecture, I'm just going to be going over the output. So come to that if you want. Don't come. It's okay. Just as a reminder, whatever output that you get for this SPSS, you're going to have to copy and paste it into this Word document. Don't forget that. Are there any questions about any material that we covered today or assignment number 8? Once again, assignment number 8, we'll be going over in more detail on Wednesday, but you have all the information now if you don't want to come to class on Wednesday.
Does anything in assignment 8 need to be handwritten, or can it all just be on Microsoft Word?
So literally what I want you to do is to put all the answers in here. Okay, so here's a caveat. Typically, we have you write it down because we're doing it online, typically we have you like do it by hand and then upload your hand calculations. I don't care about your hand calculations. Keep them, like I would suggest doing them by hand and keeping them written down, because if you do something wrong, I'm going to be able to say like, oh, here's maybe what happened by looking at your handwritten work, but I'm not going to require that you upload it because I don't want to sift through it all essentially. But I would suggest keeping your handwritten work, so that way if you do something wrong, I can look at it and we can see where you went wrong. That was a good question. Any other questions? Oh, I sent you an email earlier today about midterm peer evaluations. Fill out that Qualtrics survey. Won't take you that long. It's just one question per person. The way it's set up, I couldn't figure out how to do the skip logic. So you just put your first name, you put your name, first and last name, as well as what group you're in, and then just skip each page until you get to your group number. Like it goes in order, group 1 through 6, 1 through 5. You'll see it, you'll understand one question about each group member. This is going to be calculated, and I'm going to average up the scores, and it's going to be part of your midterm peer evaluation grade. If you don't do it by Wednesday, whatever time I said, maybe 3 p.m. I think, if you don't do it by then, you get an automatic 0. So please make sure you fill it out. Won't take that long. Any other questions, feel free to stay after class and talk with me about it. Otherwise, I will see you potentially on Wednesday, but definitely on Friday. All right, have a great day.